Welcome to Biochem Bootcamp. Here in Chem 567, we have discovered that many of you have actually forgotten your basic chemical calculations that you learned in Chem 200 and Chem 201. So we're going to be reviewing the things that you have previously learned so that you can succeed on exams. And on every single exam, we're going to have a Henderson-Hasselbalch question, and we're going to have a basic chemical calculation question for you to make sure that you remember how to do this, because many of you want to get jobs in the biotech industry, and the biotech industry expects you to still remember all of those basic chemical calculations that you learned back in Chem 200 and 201. So today, we're going to start with percent solution. And percent solution, it's important to pay attention to the units that are given. In percent solution, you can have a weight volume solution. And this is the kind of thing you might have if you were making up a solid and putting it into a liquid. You have a certain number of grams per 100 mils total. You can have volume. Let's say you wanted to dilute some ethanol. You can take a certain number of mils and bring it into 100 mils total volume. Or you can have a weight. Now, weight's very often used in analytical chemistry, maybe a little bit more than in basic biochemistry, but still it sometimes is used. And that is grams per 100 grams. So let's specify that when you are doing percent solutions, you do not need to use the molecular weight. Now, this is an important idea because I once had a Chem 567 student who went for an interview with a biotech company, and very often when you go for an interview, they give you a little quiz at the interview. And so she came back to me and she said, "Oh, the interview went absolutely fantastic. You know, they gave me a quiz and I did it, and I did really well on it." And I said, "Well, what were some of the kinds of questions that they asked you?" She said, "Oh, well, they gave me a percent solution, and so I took the molecular weight of, you know," and I was like, no, because with percent solution, you don't need molecular weight at all. It is strictly grams per 100 mils, mils per 100 mils, or grams per 100 grams, part over the whole. So if you have a 6% sucrose, weight volume, because sucrose is a solid, so you'd need weight up there, and you wanted to make a 6% solution, you would have 6 grams per 100 mils. On the other hand, if you had liquid ethanol, 1% ethanol solution is a weight solution because they're both liquid. And when we say that in biochemistry we're making a solution, we are generally assuming that everything is aqueous. So everything's being brought up in water because this is biochem, not organic or something like that. So if we're making a 1% ethanol solution, volume, it's 1 mil per 100 mils total. On the other hand, if you wanted to make a 1 molar tris solution, for a 1 molar tris solution, now you would need the molecular weight. So the molecular weight of tris is 60.3 grams per mole. And if you wanted to make a 1 molar solution, that would be 60.3 grams per liter of solution. And then you can just adjust these. So if, for example, you wanted a 0.5 molar solution, you would say 0.5 instead of 1 molar here. Or if you weren't making up a complete liter, you'd say, "I'm only making up a half liter." Well, then you can multiply this by 0.5 liters to get, the 30.15 grams that it would be if you were only making up 500 mils. Now, also, when you are doing solutions in biochem, very often you use dilutions. And my favorite equation for dilutions, M1V1 equals M2V2. Some of you have seen this as C1V1 equals C2V2. It's the same idea. Basically that there's a certain molarity or concentration, and this works for molarity or it works for percent solutions, which is why people say C1V1 equals C2V2. And there's a certain volume. So you put in what you know and you solve for what you don't. So if you have a 4 molar solution of sodium chloride and you need 2.5 liters of 0.3 molar solution. This is a straight dilution type of calculation, so you're going to use M1V1 equals M2V2. So you say, well, what do I know? Well, you have 4 molar, so you know what you're starting with. You know what you need. You need 2.5 liters, so you know what you want to end up with. And you know that what you want to end up with is 0.3 molar, so that's also what you're going to end up with. So you're solving basically for V1. Now, stop the video right now and solve this problem. Make sure you know how to do this. So whenever I give you a problem in this video, you should turn it off. As soon as I show you the problem, you should pause it so that you can see, you know, the problem, and then try it at home. Because it's only by trying it at home that you're going to know whether you are truly prepared to see this on an exam. Because I find that when my Chem 567 students actually try this at home, this spurs them to crack their old Chem 200 and Chem 201 textbook and say, I better start learning this stuff now because I'm going to see it on an exam. So if you did that, hopefully, you would then say, put in the 4 that you know, the 0.3 and the 2.5 that you know, and solve for the V1. And V1 equals 0.1875 liters. That's how much you'd have to start with of the volume of the 4 molar solution, and to be able to get 2.5 liters of 0.3 molar solution. And of course, to that 0.1875 liters, you're just going to add water to make a total of 2.5 liters total of solution. Now, this question can be asked many different ways. It can say, here's how much volume I have, and here's what I want. What's the starting molarity that I need to make? Or it can say, how much volume can I make? Or what would the end molarity be? So it's not always going to be exact wording like this. Sometimes we get a little bit tricky with the questions, and we'd say, okay, well, here's your starting molarity and your starting volume, and you know, here's the volume you want to end up with. How much water would you need to add? And in that case, maybe you're solving for, you know, a particular volume, for example, and then you'd have to say, oh, but here's what I want to end up with, and here's what I'm starting with. And if the question asks how much water, then it's the difference between the two. So it's always very important to pay attention to the exact wording of the question and not just say, oh, I know how to do this. Okay, so always make sure that you are paying attention to units as well. Now, when you are working with units, sometimes we might throw density into the mixture or throwing a molecular weight into the mixture. So we can do things by following the units. If you have density, maybe density is in grams per mil, a very common unit for density, and you're given the molecular weight for something. So then you can say, well, grams per mil divided by grams per mole, and now I have moles per mil. Well, maybe that's not a useful unit for you, but maybe molarity is. Well, moles per mil to moles per liter, you should know the metric system, so you should know how to change those units. So let me give you an example of a problem that uses this. And I'm going to read this to you because I know on video this is going to be kind of small for you to see. So it says, you need to make a solution which contains 1.4 molar beta-mercaptoethanol and 2% SDS. Now, this is an actual previous exam question. So this is the level of difficulty that you're going to see on exams. We're not just going to give you very simple things that only require you to use M1V1 equals M2V2. We're going to throw in extra information and multiple calculations for you. So you need to make a solution which contains 1.4 molar beta-mercaptoethanol and 2% SDS. You're given one bottle marked 10% SDS and one bottle marked pure beta-mercaptoethanol. Formula weight's the same thing as molecular weight, 78.13, density 1.11 grams per mil. Calculate the number of liters of each that you need to make 1.6 liters of the solution. Now, this was based on a question I got from a graduate student in a lab that I was working in who, had this same kind of problem. They had beta-mercaptoethanol, and it did not tell them the molarity of the beta-mercaptoethanol, but it told them the formula weight and it told them the density. And so they came to me and said, Kathy, I don't know what the molecular weight of beta-mercaptoethanol is. Well, aside from being able to easily look it up, I said all the information that you need is right there on the bottle. You just have to know how to use units. So if you're not in a good place or during an exam where you can't look up the molecular weight of beta-mercaptoethanol, you have the tools needed to figure it out. So remember, you're making a solution which has 1.4 molar beta-mercaptoethanol and 2% SDS. So you want to stop the video right now, those of you watching, and do this calculation. Actually try doing this calculation. So when you have this problem, the easiest thing to do first is the SDS. And in the SDS, it tells you that you're starting with 10% SDS, but you don't know how much of that 10% you need. And you know you want to end up with 2% SDS, and you know that you want to end up with 1.6 liters of it. So you can put that very easily into the M1V1 equals M2V2 calculation. And it tells you you need to start off with 0.32 liters of the 10% SDS. So you're going to put 0.32 liters in a total of 1.6 liters volume. Now, when I say in a total of 1.6 liters volume, don't start by putting 0.32 liters and bringing it up to 1.6 because you still have the beta-mercaptoethanol to worry about. So remember that I just told you that you can take the density and the molecular weight and use that to figure out the molarity of something. So the density was 1.11 grams per mil. The molecular weight was given as 78.13 grams per mole. So this is 0.0142 moles per mil, or when you convert it into liters, 14.2 moles per liter. Beta-mercaptoethanol is a 14.2 molar solution. So now that you have all those units out of the way, now you can just use it as a straight dilution problem. So that straight dilution problem then becomes, you're starting with 14.2 molar. You don't know how much of it you need, but you know that you want to end up with 1.4 molar and 1.6 liters of it. So you need to add 0.157 liters of beta-mercaptoethanol. But if I was to make this problem tricky and I'd say something like, how do you make this solution? Then the proper answer would not be 0.32 liters of this and 0.157 liters of that. It would say plus this, plus water to a total of 1.6 liters. So again, you have to pay attention to the wording of the problem to see exactly what is being asked for in the problem. Now, there are other equations that you will be using this semester. One of the other equations that you will be using many times this semester is Beer's law. And Beer's law says that the absorbance is the extinction coefficient times the path length times the concentration. Now, absorbance itself has no units. So when you need to use absorbance and you need to relate the absorbance to something else, you are relating it to the various units in the extinction coefficient, the path length, and the concentration, or you're relating it to something else that's a known concentration, for example, as when you make a standard curve. And we're going to be talking about standard curves later in the semester. But for right now, the extinction coefficient is a constant for whatever you're measuring. In your first experiment, you're going to be using the extinction coefficient in a formula to be able to multiply to find the concentration. You're gonna determine the absorbance, and you're gonna use the extinction coefficient to find the concentration. So the extinction coefficient is gonna have some units like per molar per centimeter. The path length, a standard cuvette in this class and in many other places, unless you're using a particularly small micro cuvette, which can happen when you're doing biochem research and you have restricted supply. They make cuvettes that are much narrower than normal, but for this semester, we're going to assume our path length is always 1 centimeter. And the concentration then would be in molarity to allow the molarity to cancel out like the centimeters are canceling out. And so absorbance itself has no units. So remember that for our first experiment this semester. Now let me start talking about pH. And so again, I'm going to read you this because I know that the print is going to be very small on the video. A buffer is a solution of a weak acid and its conjugate base. It resists pH change when there are reasonable amounts of both forms present. A buffer is best when used close to its pKa. Buffers are made by taking a weak acid and titrating with a strong base until the pH is correct, or taking a weak base and adding strong acid until the pH is correct. A buffer can protect against pH changes from added hydrogen ion or hydroxide ion as long as there is sufficient basic form and acid form respectively. As soon as you run out of one of the forms, you no longer have a buffer. Now this should all be a review for your basic chemistry. So if you've had your year of general chemistry, you should know all this stuff already. To be a good buffer, the pH of the solution must be within 1 pH unit of the pKa. And the pKa gives an idea of the strength of the acid and tells us what the pH will be when there are equal forms of acid form and basic form present. So, like I said, for the basic chemical calculations, you're going to have problems on exams using the Henderson-Hasselbalch equation. Now, in case you do not remember Henderson-Hasselbalch, here it is right here, that the pH equals the pKa plus the log of the conjugate base over the conjugate acid. And this can be in, it will work out if it's moles, it will work out if it's molarity, but you do need to use the same units. If you have moles here, you need moles here. If you have molarity here, you have molarity there. So you need to make sure the units are the same so that they'll cancel, but other than that, it's a very useful formula. So the question, what is the pH and molarity of a buffer prepared, and I'm sorry, I know I have bad handwriting, by adding 20 mils of 0.2 molar sodium hydroxide to 50 mils of 0.1 molar acetic acid. And we're going to say the pKa in this case is 4.76. So you already know the pKa, and you're finding the pH, which means you need to work on the conjugate acid and the conjugate base amounts. And you also need to work on the molarity of the buffer. So there's 2 questions in one here. So now is the time for you to stop watching the video and try to do this on your own. So to start, at first, you have 50 mils of the acid form. So it tells you right here that you have 50 mils of the 0.1 molar acetic acid. So 50 mils times 0.1 molar, you have 5 millimoles of the acid form. And then you add 20 mils of 0.2 molar sodium hydroxide. So you're adding 4 millimoles of the base. When you add 4 millimoles of the base to the acidic form of the acetic acid, you are converting 4 out of those 5 millimoles of the acidic form of acetic acid to now the conjugate base of acetic acid. So you still have 1 millimole of the acetic acid, 1 millimole of the HA left, and now you have converted 4 millimoles of that to your A minus to your conjugate base form. So now you can put this into the Henderson-Hasselbalch equation. So when you do this, the pH is 4.76. We've said that was the pKa, plus the log, not natural log, log base 10, of 4 millimole. And if you want to use it as a concentration, it's in 70 mils total volume, because you had 50 mils plus 20 mils, or 70 mils total. But here's the thing, these volumes cancel out. So you can just use the millimoles of each and you're still going to get the same answer. That's fine. So 4 millimoles of the conjugate base, 1 millimole of the conjugate acid, and then do the log of that, and then add it to 4.76, and your pH should be 5.36. So you're halfway there. You've solved half the problem. So the other part of the question was, what is the molarity? So to get molarity, you still have 5 millimoles total. When you are doing a buffer, you can have some of your form in the conjugate acid and some of your form in the conjugate base. So you still have a total number of millimoles, or moles, you know, if you're working with moles, but you still have a total amount, no matter how they're converted, as long as you have significant amounts of the conjugate acid and significant amounts of the conjugate base, basically a 10-to-1 ratio, because once it gets beyond that 10-to-1 ratio, it's going to be more than 1 pH unit away from the pKa. So as long as you're within a 10-to-1 ratio, you're going to have significant amounts of both the conjugate acid and the conjugate base. So you have a total of 5 millimoles of both of them in a total of 70 mils. And you're converting this to liters because you're interested in molarity. So you have 71.4 millimoles per liter, which is 0.0714 molar. So that's how you would solve a multi-part problem. And you're going to see problems like this on the exam. Another type of problem that we can give you is a 0.2 molar acetate buffer, which is pH 5.0. And we want to know, well, if we have a 0.2 molar acetate buffer that's pH 5, and if the pKa, we're saying the pKa of acetate right here is 4.77. I know I said 4.76 a minute ago, but I just used 4.77 for this problem. And we want to know, you know, what's the relative concentrations of these? Now remember, once you already have it as a buffer is saying you have, at that pH 5.0, you have concentrations of the acid form and the basic form. So you should be able to figure out what is the relative amounts of both of them just by knowing the pKa and the pH, and basically working the problem backwards. So this is the time you want to stop the video and listen to it again if you need to. Try it yourself before you resume the video. So under the assumption you've done that, you're going to put in what you know into the Henderson-Hasselbalch problem. So you're saying, okay, this is my pH, this is my pKa, and I have log of the conjugate base over the conjugate acid. So when you subtract 4.77 from both sides, you say, okay, 0.23, that's the difference here, is equal to the log of the conjugate base over the conjugate acid. Well, then you need to take the inverse log of both sides. So the inverse log of 0.23 is 1.70. The inverse log of A minus over HA is just A minus over HA. So you have A minus over HA is 1.70. In other words, basically, we're saying there's 1.70 times as much of the A minus as there is HA. There are different ways of solving this problem. One way of solving this problem is saying, okay, well, let's just say we have X, and we're going to let X equal our A minus concentration. X equals the conjugate base concentration. And we know from the problem above that we had a 0.2 molar solution. So 0.2 molar was the conjugate base and the conjugate acid. So 0.2 minus X equals the concentration of the conjugate acid. So two things to note here. I'm working with molarity here because it was molarity in the problem above. Remember last problem I was working with millimoles. So you have to keep your units straight. So this time I'm using just molarity because it was easier. And I'm saying I'm not working in millimoles. I'm just saying a conjugate base and conjugate acid with the units of molarity. Okay, so 0.2 minus X equals HA. So then you're going to go ahead and do the math on it. You're gonna put in what each one is. So you'd said let X equals the A minus, let 0.2 minus X equals the HA. So you're gonna substitute those in. 1.70 equals X divided by 0.2 minus X. You're gonna cross multiply. So 1.70 times 0.2 minus 1.70 X equals X. And then get all the like terms on the same side of the equation. This is just the basic algebra, which I would hope, being ready to graduate from college in chemistry, that you can do algebra. So 0.34 equals 2.7X. So X equals 0.126. And then you go back and say, well, we defined X previously as the concentration of our conjugate base. So remember last time we'd said we defined, we were working with conjugate base as millimoles, but this time we're actually working with molarity. So 0.126 molar is our concentration of our conjugate base, and 0.2 minus 0.126 is 0.074. So that's going to be the concentration of our conjugate acid. So you should practice equations like this because you're going to be seeing them all the time on exams. Next lecture up is going to be protein purification lectures.